Okay, Unit 4. Here it's just identifying quadratic expressions. We recall a quadratic expression looks like this if you simplify things out. There's an x squared term, there might be an x term, and there might be a constant term. So a cannot equal 0. You have to have that x squared term, but b can be anything. B or c, anything, which also means 0. Okay, so for this first one here, clearly there's an x squared term and doesn't need anything else. So this one is definitely quadratic. Here we see that the a term is 3, so we have the x squared term, but we're also allowed to have an x term and a constant term. So this also would definitely be quadratic. Here, it looks like it could be quadratic because it does have b equals 10. But the problem is that we can't have the x squared term missing. This would just be considered linear. So this is going to be no. This one, well, each of these terms are quadratic, but when you multiply them together, like if we started to FOIL this, you'd see that you'd get an x to the 4th term by multiplying those first terms plus some other stuff. So that right there is going to make this not quadratic. Here, don't be tricked. We have an x squared term, but it's in the denominator. If we actually rewrote this with negative exponents, which you should be able to do, that would be 3x to the negative 2 power, which is definitely not quadratic because it's not squared. It's to the negative 2 power. So no. Here we have a nice x squared term, but we have to look at what the other stuff is. The only other things you're allowed to have are a linear term and a constant term. Well, this is a square root term. If we rewrote that piece with fractional exponents, it would be 2 to the 1/2 power, sorry. So this is the piece that makes it quadratic. And here, this one you have to do a little work. We can probably recognize that it's going to be quadratic, but if we actually multiplied it out, x minus 1 squared is x squared minus 2x plus 1. 2x squared minus 4x plus 2. And we can see that when we write it in the more familiar looking form, it definitely is quadratic. And then here, too, we have to multiply that out. We have x squared plus 10x. Again, we have an x squared term, and the other stuff that we have is legal. It's just a linear term. So that also is quadratic. For the graph shown, sketching the vertex. Well, remember the vertex is the turning point on the parabola, so right there is going to be our vertex. Line of symmetry is the line that actually goes through the vertex. It's if we could fold over this parabola, would it fold on top of itself? So that's the line of symmetry. Coordinate of the vertex here. Well, we can see that the x-coordinate is 1 unit over. Y-coordinates up here at 15, 16. Equation of the line of symmetry. Well, vertical lines always have the equation x equals something, right? Y can be anything, but x is always fixed here, so it looks like this is at 1. So the equation of the line of symmetry is x equals 1. Zeros is where the graph intersects the x-axis. So we have those coordinates here. Let's see, negative 3, 0, and 1, 2, 3, 4, and 5, 0. So there's 2 zeros on this parabola, or 2 zeros. Provide the coordinate of the y-intercept. Just going to check out where that right there. So we know that the x-coordinate always is 0 with the y-intercept. 0, 15. Given that a equals negative 1, write an equation for the parabola. Well, one approach would be to use intercept form. We know intercept form is a times a times x minus one intercept times x minus the other intercept I've told you that a is negative 1, and so we can just go ahead and look at the intercepts. One intercept is negative 3, so x minus a negative 3, and the other one is 5, so x minus 5. If we finish simplifying that, we get x plus 3, x minus 5. And showing that it's correct, we can just pick another point. Let's see what f of 0 is. Make sure we get the y-intercept correct if we do this. We throw 0 into here, we get negative 1. 0 plus 3 is 3. 0 minus 5 is negative 5. And we get 15. So indeed, we do get the y-intercept. So we're pretty confident that that equation is correct. You could have also approached this with the vertex form. Vertex form, if you recall, is a times x minus h squared plus k. I've told you that a is negative 1. The vertex, the x-coordinate of the vertex is h. That's h right there. This is k right there. So we can get x minus 1 plus 16 all squared. And you could validate this in the same manner. I'm not going to go ahead and do that for this video. But either of these answers would be acceptable. So factoring. When you don't have a trinomial, really the goal in factoring, when it's just a binomial, is to see if you have some common terms. Here I can see that we have an x in both terms, so that's what I'm going to factor out. X times x minus 5. And if I just to see if they're right, I could redistribute that back out, which equals x times x is x squared, x times negative 5 is minus 5x. So it looks like I've done it right. Here, this is what William likes to call triangle square. So we're trying to find two numbers that multiply. Well, here, I think that's what two numbers that multiply to negative 18 and two numbers that add to 7. Do a little work here. We can see that those numbers are going to be 9 and negative 2, and so those are our factors. X plus 9, x minus 2. And if you wanted, you could remultiply that out to see that we did it right. Maybe do that one time here. X squared, the outer terms are negative 2x, inner terms plus 9x, last terms minus 18. You get x squared plus 7x minus 18, which is what I started with. So again, that's the right answer. For C here, two numbers that multiply to 9, two numbers that add to negative 6. Well, see, negative 3 and negative 3 will fit that bill. So we have x. So those are the factors, x minus 3, x minus 3. Those are the numbers that are just dropping down right there. Here we have just two terms. So goal is to factor out something common. In fact, that should actually be our goal with everyone, is to see if there's a common factor we can just take out. Here we see that 3 is common to both of these, so I'll take that out. 3 times x squared minus 9. And then we may notice that this is also factorable. If I can find two numbers that multiply to negative 9 but add to 0, we know that we can see that 3 and negative 3 will fit that bill. So to finish factoring this, we get x minus 3, x plus 3. And the last one here, start out by noticing that there's a common factor of 2 in all these things. So we're going to take out that 2, x squared plus 4x plus 3, and then we'll see if we can factor that. Can we find two numbers that multiply to 3 Put add to 4. Well, yes, 3 and 1. So then we can finish factoring this as follows. 2 times x plus 3, x plus 1.